We're really excited to talk about some really cool stuff. We've got amazing experts and scientists on the panel today, so it should be pretty fun. Okay, we'll just go ahead and get started then. So, welcome to the Cosplay for Science Creating New Worlds panel. We're really excited because we brought some really amazing scientists to talk to all of you about how the amazing universe that we live in inspires so many different universes in the multiverse. I like to say that everything in real life is stranger than anything you'll ever see in fiction. And I hope you kind of see that today as we go through some amazing worlds in the multiverse and share how real they could be, how plausible they could be, and also some of the cool things we're learning in science today about the real world outside of our own system. So really quick, Cosplay for Science is an amazing initiative. We are a group of scientists, we're a group of cosplayers and educators, and we love to combine all of those things to share the amazing stories in science with all of you out there, helping you learn to ask the right kind of questions in the different kinds of movies and worlds. So like I said, we have amazing panelists here today, so let's go ahead. Oh, I don't know. I didn't connect to the internet, I'm sorry. I don't want to pay for it. So we have an amazing group of scientists today, so why don't we go down the line, everyone kind of introduce themselves, tell us what you do, and what your favorite fictional world is. Let's start, Phil?
I'll start. Hey, so I'm Phil Boan. I'm a paleontologist and planetary scientist at the University of California, Riverside. My research focuses on early animals and also impact craters on Mars, so they're widespread. And my favorite planet is Arrakis. Big spice guy.
Hi, I'm Adriana Rizzo. I'm an organic geochemist, also at UC Riverside. So what that means, I study organic matter, that's carbon-based stuff in nature. Since life on Earth is made of carbon, this means I'm basically studying ancient life. So my research is on the evolution of life before animals and very early Earth. But also interested in, we can also use the same methods to understand carbon outside of Earth and maybe how likely is there to be life on the ingredients for it in various other extraterrestrial bodies. My favorite fictional planet is probably Solaris from Solaris, the planet that makes everybody go insane.
It's grad school.
Yeah, exactly.
Grad school planet.
Yeah.
Hi everyone, my name is Leung. I am also a grad student at UCR. I work on planetary atmospheres, and I'm specifically interested in signs of life in planetary atmospheres and how we could detect them from afar. And my favorite fictional planet is Tatooine.
Hi, I'm Wynter Broussard. I am also a graduate student at the University of California, Riverside. I study similar things to Michaela. I study planetary atmospheres and hazy worlds, and basically what terrestrial planets look like around different stars. And I don't know if this counts, but my favorite fictional planet is Discworld.
Ooh, very nice.
Hi everybody. My name is Woolley. I'm a PhD candidate at the University of Southern California in the Earth Sciences Department, and I also am a graduate student in residence across the street from USC at the Natural History Museum of LA County. I'm a vertebrate paleontologist, and I study reptile evolution, mass extinctions, and how to use various kind of methods to understand the fossil record as a vertebrate and its quality. I'm excited to talk to you about it. And my favorite fictional world is Arda, home of Middle-earth.
I'm James Keane. I'm a research scientist up at the Jet Propulsion Laboratory in Pasadena, California, and I'm a planetary geophysicist. I study the interior structures and surface geology of planets and moons in our own solar system. And as part of that, I am involved in NASA missions like the Juno mission that is currently orbiting Jupiter, and the New Horizons mission that flew by Pluto and some Kuiper Belt objects. My favorite fictional planet is probably Andoria, where the Andorians are from in Star Trek.
Very nice. Well, welcome to all of you. Can everyone hear me? What if I just talk like this? Okay, good. I can talk louder if I need to. I'm very loud. So let me introduce myself. My name is Gabriel Santos. I am the co-founder of the Cosplay for Science initiative. but I'm also I work at the Raymond Alf Museum of Paleontology. We're located in Claremont, about 40 minutes from here. I am the director of education at the museum, so I like to take everything that I do from, I used to study marine mammal evolution, talking about conservation today, anything that involves around natural history and science, sharing it with my museum. I'm also currently a Grosvenor Teacher Fellow with National Geographic and Lindblad Expeditions, and I really, really love to be able to share so many amazing stories. And that's why I brought all these amazing people here today. And this panel is brought to you also by UC Riverside's Earth and Planetary Sciences Department. Did I do it right?
Yeah.
Okay, cool. So let's get started. Why don't we just go ahead and explain to everybody who may not be familiar, what exactly is planetary science? Does anyone want to give that a go first?
I mean, we got a guy from JPL.
Oh yeah, I was watching everyone look at me. So planetary science, I'll just informally define it, is the study of planets, shocker. It's a very interdisciplinary science. It involves everything from chemistry to geology to physics to biology and everything in between to understand how planets, planetary moons, small bodies of asteroids, comets, even some aspects of their stars and the gases and particles around everything, how they all work as a system. And planetary science both includes studying things in our own solar system, so like the planets like Earth, Mars, Jupiter, that sort of thing, but also exoplanets, planets around other stars. And exoplanetary science has been very exciting because the number of exoplanets that we know, your exoplanetary folks actually know the number off the top of their head, has just gone.
It's a little over 5,000.
A lot has exploded in the last decade or so. So it's a very exciting field. If you all want to add to it.
Yeah, I typically think of planetary science as kind of being the place where, the study of the structure of a body, the atmosphere, if it has one, and biology kind of all intersect, and that's kind of the way that I usually think about it, is that these different systems all interacting kind of in an integrated way.
Sound good?
Yeah,
I agree.
And I think one of the things I like to talk about is, we talk about science in this very, very specific way today, with lots of data and history and all this thing that go into the way that we experience and understand the world. But the cool thing is that some of the earliest science, some of the earliest explanations of the world around us are just these stories that are passed down from culture to culture, person to person, that explain the reason for the stars, the planets that are out there. And they have in turn inspired so many amazing stories, even though we didn't know that much about the world outside of our own solar system. And that's what we're going to do today. We're going to look at some of these stories that were inspired by what we do know about the world around us, that are these just amazing, amazing and fun fictional planets. So let's actually head over to the multiverse, and we're going to look at a few planets today. The first one we're going to actually look at is Phil's favorite planet. We're going to head over to Arrakis. So as we all know from Dune, if you've read the book or watched the movie, which I did because I have terrible reading. So Arrakis, this desert planet, it's known for spice, which is a mineral?
It's an organic compound.
It's an organic compound that's they use throughout their version of their galaxy, and it's got the sandworm, lots of different cultures. For all of our panelists, Arrakis, is something like that, could that exist in our world today?
Yeah, go for it. Yeah.
I was just gonna say, Arrakis has a lot of similarities to both some environments on Earth as well as Mars. Arrakis is kind of based, like the whole Dune world is kind of based on the cultures of the Middle East on Earth today, and a lot of the broad strokes of the climate and environments we see on Dune are sort of similar to desert climates on Earth. And of course, Mars is a very famous desert planet that's very dry and has these dust storms and lots of sedimentary rocks. So yeah, in that very overall broad way, yes, it is. It's plausible, but You want to say more, Phil? I know
I-
you have more to say about this.
I mean, yeah, it's certainly a plausible world. It orbits a real, like, the star that it orbits in the book. It's like an actual star. And I do think they found a hot Jupiter in that system, but not a terrestrial planet. So around that star system, which I'm blanking on the name of the star, I apologize, but they have yet to find the actual Arrakis. But it's an interesting book in the plausibility because it's ecologically based. You have two organisms, sapiens and then the worms, competing for the same ecospace, which is Arrakis. And both of those taxa, if you're viewing it from an ecology point of view, both those taxas are manipulating the ecosystem for their benefits. And you can see this both in how they're responding to resource allocation, but also how they're spatially distributed. The sapiens are clustering in small sietches, trying to get water as much as possible, while the sandworms are living abundantly throughout the desert, feeding on plankton. Right?
Yeah, so the sandworms feed on sand plankton,
Yeah.
which is pretty similar to how marine ecosystems work today. You have very, very tiny organisms that are the base of the food chain that much larger organisms eat, sort of like you've heard of a whale shark. Those are enormous, or most whales are like this, enormous animals that feed on tiny microscopic plankton. So the sandworms are really just like a version of that. And you can even see that when you look into the mouth of a sandworm. They have these terrifying mouths, but they're full of these really with very thin teeth that almost look like baleen on a whale. If you've ever seen that, it's more like a brush than actually like teeth.
I'm sorry. Keep talking. I'm going to turn off my Wi-Fi.
Yeah, so the whole ecosystem is really a very simplified version of kind of a marine ecosystem, where you have these two basic animals in the system, and then the humans and this third interloper. And the humans are kind of competing with the sand plankton for spice, which is, both of them want the spice. And so there's kind of a parallel there to the way humans have can be an interloper in marine ecosystems and how we've altered marine ecosystems through fishing.
Looking at Arrakis, there's populations on there. It seems to have a breathable atmosphere, but we look at a planet like Mars, right? Doesn't seem like it has a great atmosphere, as we've kind of know in the general public. Why is it that someplace like Mars doesn't have a great atmosphere? Meanwhile, something as Arrakis that looks very similar as a planet environment, that looks like it can have a nice breathable atmosphere. What would be the difference there, you think?
So this comes down to a couple of things, in my opinion. One of which is so the reason why Mars is largely thought to be the way that it is because it's further from the sun than Earth, and it's pretty small, which means that it is easier for gases to escape and for the atmosphere to kind of dissipate out into space. So for Arrakis, even though it has a similar climate, we're talking about maybe a closer in distance, so it's not cooling off so quickly, and then potentially also a larger size, so that it doesn't have everything escaping to space. I also think what we were just talking about, which is the coevolution of the sandworms and kind of the environment on the surface of the planet, really does influence that, because everything that's in the atmosphere has to come from somewhere. And we know that Arrakis did previously have, I believe, wetter periods, and so you could potentially also generate an atmosphere from that water, from volcanoes, from things like that. And that is one of the problems with Mars, is that the atmosphere is going away, and there's no processes to regenerate it. And so that's, in my opinion, kind of how those factors break down between Mars and Arrakis.
I just want to add on. One, it's not your opinion. You're scientifically very accurate. You brought up how planets can change over time. It's worth noting that Mars, what is believed to have had water on the surface in the past and a thicker atmosphere. There are ancient water bellies carved into the surface, ancient lakes, some of which are currently being explored by NASA rovers. So this theme of how planetary climates change is seen in our own solar system today.
Awesome.
By the way, that is a picture of Mars up there that is currently standing in for Arrakis.
There's only so many photos on the internet that I can take for free. So yeah, you caught me. We're gonna move on to another planet now. We're gonna move from somewhere dry and desolate. We're gonna move to somewhere that's, beautiful, lush. I know some of you out in the audience love this actually moon. Sorry. We're gonna move to Pandora, right? From the world of Avatar. So in Avatar, humans have found this moon. It's filled with this amazing element, unobtainium, right? Okay. And it's a beautiful, beautiful, lush, biodiverse world with so many unique organisms and creatures, and it's an amazing place that's, of interest to our planet, both scientifically and monetarily. Let's not get into that part. Now, for all of us here, especially like James, you work at JPL, if we were to find a moon like this, how much interest do you think we would send there for like the science and what would we want to look at first, do you think?
Oh gosh. I mean, if we were, to find a moon around an exoplanet is very hard, and there is some speculation about possible detections, but we've not yet definitively found moons around other planets, although we suspect that they're there. It's worth noting that for exoplanets, usually when we find characterized planets, we're never going to get a picture like that from Earth or space-based telescopes. These planets are too far and too distant, so we use other methods of characterizing them. And in particular, we go after their atmospheres. So I would actually pivot back to you all about what you would want to do to characterize Pandora, our atmospheric scientists.
So it just makes me think about the way that we sort of look at exoplanet atmospheres now, which is generally via the transit method. So when exoplanets, planets transit their host star, we can sort of see differences in brightness of the host star when a planet's transiting. And so the planet's atmosphere is usually really, really, really small compared to the actual planet. And the actual planet is really, really, really small compared to the star. So it's very hard to get information from these. And I can imagine it would be even more difficult to try and get information about the atmosphere of an exomoon. I can't think of how, there would have to be I don't know if there would be a really specific transit timing that you would have to be able to get to be able to see okay, this is when we're looking at just the exomoon versus it's being hidden by planets, being hidden by the sun or so on. But
yeah, just to jump in on that, the ways that we've sort of detected these candidate exomoons that James was referring to earlier is largely through transit timing variations, and that's through very, very careful measurements of the brightness of the star, those transits that Wynter was just describing, and looking for variations in the transits which indicate the presence of an exomoon. That is already pretty difficult to do. And so getting any actual usable data out about what the atmosphere is made of or anything like that is and will continue to be very, very difficult because you have to have very high resolution and very low error. I believe Pandora is supposed to be around Alpha Centauri, and I honestly think at that point you would just have to go there, which is a completely separate issue, but that's kind of what I think, because I think if you found a moon there and you had some reason to suspect that there was potentially habitability there or even a civilization, I think you just have to go there.
Could you explain to us what transiting is?
Yes. So a transit is, this hand is say the...
Here's your star.
Oh,
Here's the planet. Why don't you describe it as I'm going?
Yeah, so you have a fixed viewpoint from the Earth, so you guys are all the Earth, and you can see as the hand moves across, the light drops. And we can actually basically measure how much light we're receiving, and so you can get a sense of how large the planet is, how often the orbit is. These are observations over long periods of time, and you can see a pattern of drops in light over periods of time.
It's kind of like an eclipse.
Yes.
Think about it like that. And one of the things I suspect you all do is, as the light gets blocked out by the planet, I mean, the planet will block out a lot of light, but its atmosphere, you can think of this as a hazy, semi-translucent thing. It will only block certain wavelengths of light that depend on the chemical composition of the atmosphere. And that lets atmospheric scientists do all sorts of fun things. So I would ask, like, what would be the things that you think we could look for in the chemistry of an atmosphere? Or what things do we look for in the chemistry of atmospheres today of exoplanets?
Yeah, so, we really think about, we often call these like biosignatures, so signs of life that we could see in an exoplanet. The most straightforward one from from biology here on the Earth is oxygen. So Earth's atmosphere is 21% oxygen. It's largely produced by living organisms. Unfortunately, there are some planetary processes that can also generate oxygen. Another gas that's often produced by life is methane. And so we often think about finding one or more of these gases. The more gases that are connected to life we find, the more likely it is that what we're seeing is life rather than a planetary process, because you would have to have the longer the string of planetary processes you have to have is to get the same signal, the more likely it is that you instead should explain this by life. We unfortunately are not in a place right now where we really have the telescope instrumentation to do those measurements. The JWST, which NASA launched last winter, will begin to sort of start observing some Earth-like exoplanets, but unfortunately we're still pretty decent ways away from really doing a thorough search for these signs of life. And that's of course for a planet, for something like a moon, you would look for the same things, but it's even more difficult to get that signal.
Yeah, the thing about transiting is it's really biased towards planets that are like really close to their host star or really big or both. So a lot of like what we know about exoplanet atmospheres, we know about hot Jupiters, like Phil was talking about, objects that are gas giants. They're really, really big, and they orbit really, really close to their host star. Some can orbit their host star in as little as like 24 hours, which I think is pretty cool. Not habitable at all, but pretty cool.
Well, talking about signs of life, if we look at Pandora for what it is, it's got amazing biodiversity and it's its own unique evolutionary pattern that we see. So for our paleontologists on the panel and biology folks, what do you think it'd be like to discover, something that that has its own unique evolutionary line there, right? And seeing that, and maybe perhaps looking for fossils when they're looking for unobtainium on Pandora, right?
Well, I think, going back to the kind of atmosphere question, like folks, the humans there, they have to wear masks. I don't remember what gas that is actually these the live animals are breathing on that atmosphere, but I think that is a kind of an interesting thing. So it's like might be different than what we're looking for, right? In terms of comparisons to Earth. I think that's what's fun about paleontology is you gotta get to go back and look at Pandora-like creatures, right, that lived on Earth. At different points, and we find on Earth all sorts of weird critters that are unlike anything that we find today. There's no modern analogs for giant herbivorous dinosaurs, right? So I think when we're thinking about some of those big flying kind of dragon-like creatures on Pandora, we gave those the names of these animals. I don't, but the sort of understanding the structure of the ecosystem on Pandora and how that might differ or be very similar to, for instance, terrestrial ecosystems on Earth today. Now, what is it? The way of the water. What's the next one?
Way of water.
The way of water. That's going to be marine ecosystems on Pandora. So that'll be interesting to sort of investigate that in our own imagination as we watch that movie.
I'm just going to plug really quick. Tomorrow we have our paleontology and pop culture panel. And one of our experts, who's actually in the audience right now, is going to talk about some of the new creatures we're going to see in the new Avatar movie. So it's going to be hype.
Yes.
One more quick thing about life, or about Pandora. They have the floating mountains, right? They have the weird magnetic, arches that they had there. Could something like that exist? Is that plausible?
No.
Okay, not to be too definitive, so my understanding is the explanation for those features is that the moon is interacting with the magnetic field of the planet and causing these sort of surface deformations, but I'm pretty sure if your magnetic field is that strong, it would also kill anything on the surface. So I don't think that you can have both life on the surface and those magnetic field line loops.
Sorry, James Cameron.
Okay. Well, that made me sad.
Sorry, again.
It's okay. It's okay. That's why it's fantasy. That's cool.
Well, and that's why we would have to go there and then discover them and then figure out how they perform.
I like James's way of thinking. Okay, so speaking of fantasy, we've talked about a lot of science fiction planets. Now we're going to move into the real realm of fantasy. We are going to go travel to Middle Earth, Arda, the world of hobbits and the Maiar and the Valar. And I'm actually going to pass it on to my good Melon, Hank, who really has been excited to talk about some of the geology and planetary science of this fantasy world. Hank?
Right. Well, thank you, Gabe. And we've been talking about this for months, and I really appreciate you having me on to talk about this. I think what makes Arda, Middle Earth, kind of a really cool, unique world is sort of the background of the author that created them, right? Tolkien was a linguist, and he created this world to sort of figure out where people who spoke these languages he created, where would they live, and what's the landscape in which these peoples lived. So it's a different sort of way than thinking about creating Arrakis or Tatooine. It's like coming at a world building from a cultural standpoint. So I think that's really fascinating. And I don't know if there's any Middle Earth history buffs in here, but it goes from being like a flat planet to being curved by events that happen and transpire throughout the history, from the first age to the second age to the third age to the fourth age. And I think what's really unique is when you think about that famous Middle Earth map, right? You've got the Misty Mountains going up north-south. You've got Mordor, which has got this kind of square mountain range. It's really interesting to think about sort of the physical processes that might build a world like that. Mountain building today. How does mountain building happen today? Plate tectonics. We talk about Mars. Maybe Mars isn't as tectonically active, and that might affect how we understand the atmosphere and what we know about it. We have plates colliding, and Middle Earth is very sort of made by the gods themselves, right? So there's all this sort of kind of narrative gray area in which you can create these mountain ranges. But if you're looking for a really good book to read about the sort of geology of Middle Earth, I recommend buying the Atlas of Middle Earth by Karen Wynn Fonstad. It was written in like the 80s, and it's like talks about literally the lithology, the science of stones of all these different mountain ranges and how they could have come up. So we're left to sort of take this linguistic cultural map and think about it, how it was created. And I would say there's all sorts of avenues that you can take that. One example I want to leave you all with, which I thought was really creative, is many people have inherited via lawsuits or whatever the rights to create Tolkien's world on screen. And the most recent iteration of that is the Rings of Power on Amazon. And I think one of the coolest kind of physical science, geological science aspects of that whole series was the eruption of Mount Doom, how they got Mount Doom to erupt. And they did that by opening a dam and introducing water to a magma chamber. Now, the magma chamber was open, so there wasn't a lot of pressure in there, so there's some problems there, but this is what happens on Earth too, is if you introduce a liquid, just like water, a fluid like water, to hot molten rock, you are going to get an explosion, and a really cataclysmic explosion. And so I think what the team found there was really creative and a really cool way to turn the Southlands into Mordor. Sorry if you haven't seen it, it's a spoiler alert, but Mount Doom erupts. So anyway, I really appreciate coming on board here. There's all sorts of fantasy worlds out there that might be more realistically created and more founded in sort of the natural history and sort of science that we know of the world, but I think it's kind of cool to also approach this from this linguistic, cultural perspective. So thanks for, and please, I'm done speaking. Anybody has anything to add?
Well, I know you brought up something cool that I know a lot of people have wondered, but I've never had a good answer for, is why do planets end up being like roundish? we have Middle Earth, which once was flat and was rounded. That's caused by some magical force thingy. But in our world, what is it that caused planets and other celestial objects to be like more round and not, like other shapes?
So matter is controlled by the laws of gravitation, right? And so every object is going to gravitate towards the center of mass. So when you have all of this stuff, all like condensing on to become a planet or an object or whatever, it's all going to go towards the center of mass. And when it's had enough time, you have just an object that, all of the matter inside of it is trying to be as close to the center of gravity, the center of mass, as possible. And that just, that's a circle, a sphere.
Yeah, and it's worth thinking about. So the planets are all roughly spherical to some extent. I mean, we obviously have topography on the Earth. As you go to smaller and smaller planetary bodies, they tend to be more and more irregular. And that's because the effect of gravity has been decreased. So asteroids can look like lumpy little potatoes because they're only a few kilometers or tens of kilometers across. But as you look at bigger and bigger asteroids, they start to become spherical, more and more spherical. On top of that sphericity, you have other complicating effects like geology that can create topography. The rotation of the planet will affect things, causing planets to bulge out. So the Earth actually bulge out at the equator. If you look at pictures of Jupiter and Saturn, you can see that bulge if you actually, they look kind of egg-shaped, they're squashed. And that's from rotation, but it's here, the magic is gravity.
Awesome. Well, speaking of gravity, I think that's a great segue to the next, kind of celestial thing we're going to talk about. For those who have seen, the movie Interstellar, it's very much grounded in science, and there's a lot of stuff in it that is not just inspired, but taken from what we actually have observed in our universe. And one of the things is the black hole Gargantua, which had the time dilation plan and everything. For our panel here, is this legit? Was that really well done in the movie, or is that pretty just that they took a little bit of that from real life?
It was not only well done, it was better than, it improved the state of the science, actually. So in the development of Interstellar, they actually involved some pretty well-known physicists like Thorne. So the graphic that you see there of the accretion disk, which is gravitationally lensed, so much gravity that it distorts how you see things. That view of a black hole and its accretion disk was transformative at the time. They did numerical supercomputer calculations to figure out what that would look like. Now, to my knowledge, I don't know if we've found exoplanets around black holes yet. They probably are there, maybe. They'd have to survive a supernova. So.
Yeah, I think there are a few issues with the planet that's very close to Gargantua in particular. I think the main issue with that planet, if it's is that their black holes emit large amounts of very high energy radiation, so gamma rays and X-rays, which would be pretty toxic. The planet is uninhabited in the movie, but that would also render it pretty uninhabitable, habitable for any life. To the point that I'm not sure why they would have picked it as a candidate for exploration in the first place. Second of all, all that high radiation would probably strip away the atmosphere, and that planet is covered in water, which implies that it has some sort of. In order to have liquid water, you're also going to have some kind of atmospheric weather cycling with the water evaporating and stuff like that, and that would have all been stripped away by all the radiation from the black hole.
Those gravity waves are cool, though.
Yeah, it's a really, really cool concept for a movie. I love that whole part on that planet. It's super cool, but I think there are a few issues with it scientifically.
Yeah, I was just going to say to the point that was raised earlier about if we found exoplanets on a black hole. So canonically in Interstellar, the planets are orbiting a star that is in this state. It's in this basically one exact stable orbit that is outside of the black hole's event horizon, and once you pass the event horizon, you can't really leave. So they basically are just kind of skating the absolute edge of where you can be. I think you would have to have a lot of stars fall into your black hole before you're going to get one that ends up on just the right path to end up staying in this orbit. I definitely agree with all the points that were just made as well about the X-ray radiation. I totally get that this is where the wormhole comes out, but it's like, if your best option for fleeing like a dying planet is planets orbiting a black hole, it's like there's no good options here.
Yeah. I wanted to clarify something. I said that if the planet would have to survive a supernova. I recall this is a supermassive black hole.
Yes.
So this supermassive black holes are black holes that form from effectively the accumulation of lots of black holes, typically in the centers of galaxies. Individual black holes are often formed by the deaths of supermassive stars in supernova, which could potentially obliterate all the planets around them. So it's a very wacky system. It'd be very fun, well, to watch a movie about, I guess. Not to actually explore.
So you have to make it in less than 15 parsecs to get around? Okay, fine. I thought it was going to be funny.
The tidal wave on there, though, is interesting because tides are a really important process in our solar system and in other solar systems. We don't get giant waves that look like mountains, but like the energy that comes out of tides is one of the things that keeps oceans surviving on the insides of icy moons in our own solar system. And tides are also really important for the evolution of exoplanets close to their host stars.
Awesome. Well, speaking of, we're running low on time, so I'm going to break just for a little bit. I'm sorry. We have one last planet to talk about, and this one is actually very close to home. And for a long time, it's been thought of as just science fiction. But a lot of that science fiction is, I think, getting fairly close to being science fact pretty soon. And that's on the planet Mars, our neighbor. So, for all of our planetary scientists, our paleontologists, I think the first question is, what is it so fascinating about Mars that we keep looking at? Is it just because it's our neighbor?
So Mars in science fiction is like the OG. When you have, you look back in the 1800s, you have Percival Lowell's observations of the planet, where he's saying that there was water canals on Mars, right? And that leads directly to the creation of like the War of the Worlds, which is the idea that you have this civilization on Mars, they run out of water, they come to Earth, right? And Mars is also the archetype for a lot of the desert planets, which is the idea that you have this planet that used to be very fertile, and then it dies, and then the goal of the planet is, and the people on the planet is to make it fertile again, right? You see this with the Tusken Raiders on Tatooine. You see it with the Fremen in Arrakis. You also see it from the Martians in The Expanse. Like the whole goal of the Martians in The Expanse is to terraform Mars. That's like their number one goal. That's all they want to do. And additionally, what Mars gets tied into is militarism. Right? Mars gets its name from the Roman god of war, and in science fiction, we often tie this militarism to the Martian society. Right? Like in The Expanse, they have the best weapons. They have, the top tier ships, and they're kind of aggressive. And so Mars it goes back to Percival Lowell's observations of these canals, but it has always been tied into science fiction since the 1800s even.
And for Mars, I think everyone really just wants to know how close are we to getting there? Is that something we might see in our lifetime?
Maybe. I mean, others will talk about this, but so we've been investing a lot in Mars exploration. The current Mars 2020 mission is collecting the rover. This is a robotic rover is collecting and caching samples for a sample return mission that will pick them up and take them back to Earth. I think maybe Mars is close enough to Earth. I think it takes about 7 years to get there. That like a manned mission is theoretically possible. It's not like interstellar travel where we have no real way of getting there, but it is something I think we have the technology for. It's more of a question of, is it worth it scientifically to send people there versus sending robots? And is it worth investing all of the money and all of the resources that it takes to send humans there? for what we would get out of it.
But what if I volunteer?
I think that's a great point. Like, what you have to make a really compelling case for something that humans can accomplish on Mars that can't be done by a rover. And I guess just to add a little bit of background, at the time which NASA funded the original American missions to the moon, space was much higher a national priority. Versus when you compare that current NASA funding levels, they're actually much lower, and there's sort of less, I guess, public momentum towards them. So NASA is right now trying to return to the moon, and I believe that is meant to be a stepping stone to go to Mars. And I think that is largely, honestly, just to do it, to say it's been done, and it's not clear to me like what the science case is for that. That's sort of more like a political problem in terms of like who's going to provide the money for that, who's going to stake a claim, what flag are they going to plant. So I think the question for what science can be done by humans is sort of different than like the political, like we just want to go there and stake a claim.
Yeah, so there's a lot of aspects of that that I agree with. Just to let you know what NASA's official plan is. And NASA plans are famous for changing and getting delayed by infinite amounts of time.
At 10 years.
And the amount of funding. In Apollo times, NASA's budget was between 5 and 10% of the total U.S. federal budget. At present, it's less than 0.5% of the budget. So you just can't do as much. The current plan. So hopefully you are all aware that there is a spacecraft named Artemis that was launched just recently on the SLS, Space Launch System. It's an uncrewed test mission for what will eventually be sending humans back to the moon as part of the Artemis program. Now NASA's plan is to use the moon as a way of sort of testing out these deep space exploration capabilities for humans, and somewhere where you're only a few days away from Earth. So this is why they're currently targeting the moon. It will hopefully lead to humans back on the surface of the moon in the next few years, is what they say, with more and more missions going to the moon to test out newer and newer technologies. As they're doing this, they want to also start building up a space station around the moon and things that will eventually, they believe, lead to the spacecraft that you need to go from Earth to Mars, which they're, depending on what propulsion system they're going to use, could take a few to 8-9 months or something like that. But the Mars side of the human exploration endeavor is likely 10 years or so away if NASA keeps on track, which they don't have a history of doing.
So like 20 at least.
Yeah, but to loop back to the science, that's a really important thing that the scientific community is very actively pushing up to make sure that science is incorporated into the human exploration of both the moon and eventually Mars. Because, I mean, we're a bunch of heavily biased scientists, but I think the reason you go there, one of the major reasons, is to do the science. And a single human on the surface of Mars, a well-trained geologist on the surface of Mars, could do basically everything that the Mars rover does in the time span of months, just because humans are so much better at identifying problems, at moving around physically on the surface, thinking up creatively on their feet. And that's why it's great to have scientists on the surface of other planets.
Well said. So we're running short on time, so I'm going to have to skip a couple of things. I'm very sorry. And I want to leave time for a couple of questions. So I had a few questions up here, but there's one question that I'm hoping that everyone can take a quick second to answer is, how do we, like audiences who are not part of NASA, JPL, in the research, how do we benefit from looking out into the stars? How does that affect us here on Earth?
Well, I mean, I'm a paleontologist, right? So I look down at the ground and into the rocks for my research. But I think from my perspective as a human, I enjoy looking out at the stars because it gives me a sense of place. It gives me a sense of belonging and also isolation. Like, oh man, we got one planet, and dang, we're on this little ball of dust whipping 12,000 miles an hour, through space, and that's pretty cool to think about. So that's my 2 cents.
I I mean, I just feel like it's a very, human question to ask, like, what is out there, and just, curiosity to want to know. And I think, it's cool.
Yeah, basically the same thing, but even more specifically, the work that I do ultimately boils down to the question, like, are we alone in the universe? And there's a quote that our advisor likes that basically sums up to, like, whether we are or we aren't, the result is staggering, right? Like, you can think about either of those scenarios. Either there's something else out there or there's nothing. And either of those can kind of break your brain if you think about it long enough. So I think it is a very, like Wynter said, human question to wonder, are we alone? Is there other life? Are there other civilizations? Are there other intelligent beings? So I think these are really questions that we've been wondering as a species since, the beginning of time, not the beginning of time, but you know what I mean. And so I think it's a really exciting time to be able to start thinking and answering some of those questions.
Yeah, I would say also, I think it's a really fundamental question of, philosophical question about who we are and what does everything mean. But I think beyond that, there's also we've gotten a lot of really practical societal innovations that come out of the engineering side of the space program, like all of the electronic miniaturization, that's the basis of our cell phones, all our electronics, all of that was developed for the space program. The internet, is related to, some of the technology developed for this originally back then. I think it's just, there's so much innovation and really practical stuff we can apply from this technology, because this really is the cutting edge of so many different types of technology, and there's so much that we can get from that and that apply to everyday life on Earth as well.
Yeah, like who used a GPS today? Yeah, you're welcome.
For me, the driver is the science of desire to explore. I mean, I'm wearing a Trekkie outfit, should be evident, but I want to emphasize this. When you look at NASA's budget and you hear about these like big multi-billion-dollar missions, every single one of those dollars, well, 99% of those dollars are spent on Earth. They're used to fund high-paying technical jobs that then build a workforce that I think benefits the United States and the planet as a whole. The NASA is kind of unique amongst the government agencies for that, the amount of money that it puts in and then returns. I think it's something like there's $8 of return for every $1 of expense on NASA's budget. There are technical spin-offs on everything from MRIs to GPS to dimples on golf balls. And it presents an opportunity, I think, to show the best of us. And in particular, the best of us in a global sense. How can we work with the European Space Agency, with the Indian Space Agency, the Japanese Space Agency to go after some of these big picture questions? And I think that's an exciting thing to do.
Well said. Thank you, everybody. So that about does it for our panel. We have time for about two audience questions, if anyone has any questions.
Okay, so my friends and I always laugh about Star Wars planets and how like monoclimate they are. Wouldn't that all be possible to have an actually inhabitable planet that is as monoclimate as the Star Wars planets are?
Does someone want to repeat the question?
Yeah, so the question is asking about the monoclimates of Star Wars planets, and if it's possible to have that and have that planet truly be habitable. This is a really funny question because we had a Star Wars panel this morning, and this was essentially one of the questions there as well. One of the things that we talked about on that panel is the snowball Earth, which was an earlier stage in Earth development where the planet was largely to mostly, depending on what evidence you believe, largely mostly covered in ice, and it remained habitable for single-celled life. And pretty much shortly afterwards, there was kind of this explosion of multicellularity and more complex life developing. That is not what we think of when we think of, say, like Hawk, which is like a similar environment, right? They have animals, they have complex things. But just like the Earth has changed through time, we would also expect any other planet, right? Mars has changed through time. We expect all other planets to be changing throughout time. So the answer to that, I guess, kind of is a monoclimate planet is possibly habitable for more simple life, But I think to have an ecosystem like Hoth or Tatooine or something like that, you're implying that it was previously different, which is consistent with our understanding of planet formation and evolution.
We have time for one more question. Yes.
You mentioned that a high magnetic field would prohibit life from forming. Why is that?
So my understanding is it's largely a radiation problem in the same way. So I know that one problem with the Apollo astronauts that they had to worry about is like the magnetic belts that surround the Earth. And my understanding is that it's like other forms of high intensity radiation where it drives high mutation rates, and I guess that could potentially be advantageous if you're thinking about like driving evolution. But if they're high enough, you can just sterilize. You can just like completely like destroy. You would break up. What that would look like in an Earth-like cell, I think, is you would like break up DNA until it was unusable, and then you're not really alive anymore.
Yeah, so I agree, and there's multiple parts of this, and in some cases magnetic fields are very helpful for life, and in other cases they're very harmful. So the Earth's Van Allen radiation belts, they're caused, the reason they're there is the Earth's magnetic field, and they trap high energy particles that come from the sun and outwards in the solar system. They're dangerous for the Earth. If you go to other planets in our solar system like Jupiter, Jupiter's magnetic field traps so much radiation that if you were to like stand on the surface of Io or Europa, you'd be dead in an hour. It's a challenge for a spacecraft to operate there. If you go to an extreme case, like if you fell into Gargantua or like a pulsar or a magnetar, magnetic fields can get so strong that they'll stretch your atoms into needles, and just from the magnetic field. If you put a magnetar at the location of the sun, you demagnetize every credit card on Earth. But on the counterpoint, magnetic fields can be useful for helping planets retain their atmospheres by shielding them from that radiation. And so that's one of the things that gets brought up a lot for Mars, is maybe the reason it that expedited the loss of its atmosphere is that it didn't have a very stable long-term magnetic field.
All right. Well, I'm very sorry. That ends it for our panel. Thank you all so much for joining us. Give it a hand for our amazing So, couple things. After this panel, you can come up. You can get some really cool stickers and posters from NASA. And then also, if you still have a lot of questions for us, join us at the Cosplay for Science booth down in the convention hall. We're at booth 549, and we'll be down there answering all your questions, and we have some cool fossils and Star Wars science down there. So thank you everybody so much for coming.
Thanks, y'all.